Okay, does the sound work? Can you all hear me? Of course, those who can't hear me asking. Okay. So, first of all, I'd like to thank Villanova University for kindly inviting me. I'm very honored to be here, and especially, of course, I'd like to thank Dr. Gustafsson for inviting me. So thanks a lot, and I'm happy to see so many of you present here. So what I will do is tell you first about big history, and then a little about the history of big history, and then I will continue to say more about my specific approach of big history. We will march through big history with the aid of that, and then we'll take a look at the future, because if you try to really look at big history, which is everything from the Big Bang until today, a period that astronomers now think is 13.7 million years, then of course that invites some kind of reflection on what is going to happen in the future. But I will say more about that later. First, I want to introduce you to my family. You can see us here. This was this summer. We were in China for the annual World History Association conference. Lowell Gustafsson was there also. Of course, we took the opportunity to visit the Great Wall. So here you see me with my wife, Gian Domenico, who was born and raised here in Philadelphia. So this region is not entirely unfamiliar to me, and I'm happy to be here once again. And our son and daughter, Louis and Julia. So you get an idea of my family. So first I want to say a few things about what I think has motivated my life. And I have to go back to, let's say, 1968, end of 1968, December it was, when this flight of Apollo 8 took place. Well, for you, I guess, for most of you, that's probably ancient history, but it happened. And what happened then is that for the first time in history, people flew no longer in Earth orbit, but they went to the moon, they circled the moon 10 times and came back. At that time, it was just possible to have live transmissions from the United States also to Holland. So we were watching this in Holland. There were no video recorders yet, it didn't exist. So what I did was have my camera on a tripod, and I was snapping pictures of the screen. And you see my album that I made at the time. So you see the launch, right? The astronauts in space. You had live transmissions on the way to the moon. This is the Earth that you could see. So I mean, we got really interested in what were these people actually seeing and what did the Earth look like from space. Now, at the beginning of January, then the issue of Time magazine that reached our house had this famous photo, the so-called Earthrise photo, where you see the Earth above the stark lunar surface. And that really changed me a lot. I tore it out very carefully, stuck it onto the wall. You can see the point, the hole still. I still have that copy, and it made me really think that was not like what I've ever seen before. And I was not the only one who experienced that. There were a lot of people who did that. And it changed the perception of many people. It made us aware of how fragile the Earth was, how finite it was, that there's so much black space around it. And as a result, I think many people started trying to find different ways of doing things. We were very worried about ecological problems. What were we doing to the Earth? How long would we survive? And I wanted to understand how we got ourselves into this situation and how the whole thing worked. So I think in retrospect, my life has been one long search for finding answers to that question. So it started like this when I was, let's say, 18 years old. And now, almost 40 years later, I think I have the answer. And this is a picture of, let's say, my avatar on the Wii that my daughter Julia made for me. So this is basically the trajectory that I followed. It was a long and, often, complicated trajectory. I won't tell you a lot about it, but I do think it has influenced my life to a degree that I think only recently started to understand. Anyway, now first a few big history pioneers. Here you see David Christian. He is an historian from Macquarie University in Sydney in Australia, as you can see. And in 19 '88 he started a course in what he called Big History, and it was a course organized with teachers from different disciplines. So astronomers who tell you about the history of the universe, geologists about the history of the earth, biologists about life, etc. I mean, all the way up to the present. And it came as a result of him asking, you know what, how did it originate? What actually came before that? So if you keep asking these questions of when did these things evolve, then you basically inevitably end up at the beginning of everything, the Big Bang. So he developed this course model, and out of that came a lot of knowledge that he synthesized in his book that is now a standard book. It's called Maps of Time, An Introduction to Big History, which was published in 2004. So he is a major pioneer. He coined the term Big History. He's now the president of the International Big History Association, among other things. So one of the major pioneers. But here's another one. This is Eric Chason, astrophysicist at Harvard University. He's been teaching what he calls cosmic evolution at Harvard since 1975. A long time. Most of the emphasis in his course is on the development, the origin and development of the universe, but he takes it down all the way to human history. He doesn't pay a lot of attention to human history, but it's a big history from our perspective, and he calls it cosmic evolution. He has developed a theoretical approach that I'll say more about later. The seminal book that was published in 2001 is his book Cosmic Evolution. And this picture was taken last June in his backyard, where we were invited for a barbecue. Okay, and what we did in Amsterdam was basically copying David Christian's course model and elaborated our own way. I started doing that with a sociologist, my former PhD supervisor, Johan Goudsblom. And so we started doing this course. We got a lot of students from the very beginning. We're still doing it. Every year we get between 200 and 300 students as an elective module. So nobody has to do it. But they keep coming because they find it interesting. Working really well. So here you see our astronomer at Van den Heuvel explaining the Big Bang, right? Okay. This about our history. But why would we do it? And I think the first thing to say is it answers big questions about how everything has come into being, what Dr. Gustafsson just said. That is very important. If you really want to know the scientific answers to how everything became the way it is now, that is what you need to do. Then you have to do big history. You cannot just stop 5,000 years ago, because you won't get answers to these questions. So if you want to understand our position, our current position in time and space, where are we right now, then I think it's also inevitable. You just gotta do it. And also very important, by doing that, you get some kind of an intellectual framework, a framework that you can use to attach your knowledge to. So if you start at the Big Bang, you get Big Bang cosmology, physics, all these things. Then you go down to, let's say, the solar system, the emergence of the Earth, and you get plate tectonics, geology. You get biology with the theory of evolution. And then you go down to human history, and then you get all of human history, and you try to synthesize that also. So you get some kind of a theoretical framework that you can attach your knowledge to. It's very, very useful, because so if you walk in a bookstore or a library, you pick a book and you think, you know, where would this fit? You can find a place for that in the framework. It's very, very helpful to structure your knowledge. And then if you think about all these big trends that have happened in history, then you may think, okay, some of these trends may continue, they may change, new trends may appear, but of course you cannot be sure about the future. We don't have any data about the future, but it may prepare you better than any other study for how to deal with the future. That is a claim we cannot substantiate simply because we don't have any data about the future. That may prove itself over time. But at least it's my hope. Okay, now if you think about big history, this long stretch of history, and this is a picture that was drawn by Eric Chasen and by his wife Lola, actually. That starts with the Big Bang, and then you get all these different phases of the emergence of galaxies, of stars, in our solar system, planet life, etc. The whole thing. So he calls it the era of time. And where, let's say, human history is only a very, very small part of the big picture, then you have to admit it's pretty different from traditional history. Very, very different, right? Now, the interesting thing is that if you just go back a few centuries, even I would say 160 years ago, 170 years ago, this difference did not yet exist. And I'll show you why not. Here you see, this is a Dutch world history. This is a book that starts with the story of Genesis, so the creation and everything that came after it. That's it. And then ties into that all the histories that people had learned about, so from Mesopotamia, Egypt, Middle East in general, then Rome, Greece, Rome, Middle Ages, up to the present day. So in a sense it is a big history. It's not a big history completely science-based. It's a mix between a religiously inspired story and a science-based story, because more recent themes are science-based. And in these books you have reflections about, let's say, the New World. This is the period of early globalization, that people from Europe went out all over the world and did their things, for better or worse. But they came back with a lot of information, so they were wondering, you know what, where did these people come from in the New World? Were they the lost tribes of Israel, perhaps, or what would it be? So that kind of considerations you find in these books. This is not an isolated example. To the contrary, in France, in Britain, Germany, such books were produced, and it's actually part of a long, long tradition. A tradition that stretches back into the Middle Ages and perhaps the late Roman Empire, that people started constructing these kind of histories. And the nice thing about these histories is, of course, that it answers all the big questions. It tells you where everything came from. Here you see an example from the Middle Ages, the late Middle Ages. It's not a book, it's a map actually. It's a world map, a mappa mundi, that's Latin for world map. It's in this place called Hereford. It's on a wall. This is a modern construction around it. And Hereford is here in Britain. I'll show you the map more in detail. It's basically centered around, yeah, I cannot point to two sides, I'm realizing now. So you have to look one side if you want to see my pointer. Centered around Jerusalem. This is the east is up. So here you see Britain, and this is Ireland, and this is Scotland. So Hereford, for example, is here, right at the edge of the world, more or less. And the interesting thing is not only that this is a very, it provides an idea of the knowledge that people had at the time in terms of geography, it's also a history map. So what do you see here, for example, up here? What is this here? I'll show you. This is actually Adam and Eve being expelled from the paradise. So that's just apparently, according to the map maker, that happened over there, somewhere in the east, which is up top. So there you see the biblical story, the big change that took place when people had to basically make a living. And what do we see here? This is the Noah's Ark that's stranded there on the mountain. Basically, when the whole earth was flooded, according to the story, I would describe it that someone hit the reset button, right? And basically tried to reset the whole history again, because the beginning was not very good, so let's try to all over again. Very important moment in history, according to that account. And what do we see here, for example? The Tower of Babel. That's when all the languages emerged, right? All the different languages, according to the story. So very important points in history that were elaborated, or more, won't go into that. So these maps were both geography and history. They were kind of all-encompassing, I would say. So this is part of a long tradition. You also found them here in the United States. This is an example from the 1900s. This is a book called Universal History. Starts, like all the others, with Genesis and then weaves in all the other stories. It's called Peter Parley's Universal History. Peter Parley was a pseudonym for basically a lot of writers that contributed to all these different stories. But Peter Pardy's this, Peter Pardy's that subject. I mean, it was a whole range of books. But it was probably written by Nathaniel Hawthorne, anyway. And then around 1850, doubts are starting to creep in. And it happened in the United States, for example, in this book. This is a book written by Joseph Worcester, who was a school teacher, as you can see, and I'll show you for whom it was meant. It was meant for schools in the Boston area, but also elsewhere, and also sort of required reading for freshmen at Harvard. So that's what you had to know in order to get into the university. Now, what does it say here? At the beginning, it says the modern science of geology, which basically had developed, made people doubt that actually the Earth was only 6,000 years old. It must be a lot older. So it led to a reinterpretation of the Mosaic account of creation. What the interpretation was, he doesn't say, but basically he's saying that account doesn't work anymore in terms of history. There's a problem here. So we have to do something else. Now, what was this emerging science of geology? That happened, I think, primarily because of the Industrial Revolution, when people were searching for new resources to basically use all this stuff. You needed coal, iron, other stuff to power your machines, to get the resources to make your things. So people started looking everywhere. What does the Earth look like? Can we map it? And that led to lots of more and more systematic discoveries of these layers, the old layers with all these fossils of extinct animals and plants. What happened here? I mean, there was a big problem. If you believe in just one moment of creation, then all these layers would have been created and all these fossils. Well, that didn't seem very credible. So, yeah, I mean, God could have created them one after the other, but then it must be quite a long period of time. So not more than 6,000 years. So that made people very doubtful about the, let's say, the account of Genesis. And this was still, let's say, 10 years or more before Darwin's book came out. Right? So it was not the case that Darwin's book produced this gigantic clash. It was happening already. But people didn't really know how old these layers were. There was no way of knowing that. So what you get then is in this period that people are starting to doubt the account of Genesis. At the same time, you have the period of formation of nation states. In Europe, also in here, in this, let's say, North America, also in Central and South America, by the way. And all these nation states needed their own history. Hopefully a proud history. That's a good idea. It's never a good idea to have a sad history, of course, as your own history. So if you have a country that has a bit of a problem with its history, like Australia or Peru, then you try to reformulate it a little, right, to make it a proud history. And that happened elsewhere also. So what you get is the emphasis on the founding fathers and mothers and the great things they did. And that's what these historians got paid for. That is basically what drove the establishment of the history departments everywhere. So what you get is nation states and historians who are employed to write the proud origins of these states and their supposed roots. Right? So that's how you get to the Western Shift trajectory, all the way down to Rome, Greece, Mesopotamia, Egypt. Right? And in fact, that is a very similar account that had already been produced, but with a little difference. Of course, an emphasis on literary sources, but what they did is ruthlessly cut off the biblical account. They got rid of it. So you start 5,000 years ago when the first, let's say, records appear, and the rest is prehistory. You leave it to other people. You won't bother with that because it is not important. Right? But by doing that, they also cut off all the big questions because the answers were no longer reliable. They also got rid of the big questions. I'm not really sure whether people realized it at the time. It just happened. So nobody could ask in history legitimately anymore what are the big questions, like where did we come from, where did the Earth come from? That was all beyond them. No, won't bother with that. And that led to general skepticism about big questions. Here you see, well, a revolutionary himself, Darwin, saying basically it's mere rubbish thinking about the origin of life right now. Or you might as well think about the origin of matter. I mean, that seemed like questions you couldn't answer, so you shouldn't ask them. Right? Now, what happened in the meantime is that scientific discovery continued to enlarge our ideas of space and time. I'm not going to argue that scientists were eager to answer the big questions. I don't think that was the case. But what happened is that the discoveries led to new answers to these big questions. So that made it possible in the 20th century to formulate new answers to these old big questions. Now, I'll go very quickly through that, how that worked. Let's say in around 1900, this was the dominant view among astronomers at least. We live in the center of the Milky Way that had been figured out by an astronomer, William Herschel. He had been counting stars with his big telescope at the time, and his sister was writing it all down with a candle light, so that's how it worked, right? So he made a very careful plot, and it seemed like we were right in the middle. Now the reason that he got it wrong was that there's a lot of dust in the Milky Way, so he couldn't see lots of stars, and that led to misconception. His science was sound, but he missed that. So that was the general conception. But now the situation is very different. The idea is this is our galaxy. We don't live in the middle. We live in one of the suburbs somewhere in one of these arms, and it's only one of billions of galaxies in an expanding universe. And most of these galaxies, certainly on the larger scale, are flying away from each other. Now that's quite different view, right? And how did that happen? How did he find out? And the answer is by capturing more light. That is what scientists did. Bigger and better telescopes, and very importantly, the invention of photography. So basically you could suddenly take pictures. That means you could not only capture more light, because if you just follow your star with your telescope and you keep capturing the light, I mean, you can capture more light than if you just look at it and you have to write it down like that. It's also more precise. You can do lots of measurements you cannot do if you have to do it with your own eyes. So that made the whole discipline of astrophysics possible, doing measurements with starlight. And I think especially this was the problem that led to a whole different view of the universe. Because in the galaxy there were these so-called spiral nebula. Now, nobody really knew what they were, and there were already speculations in the 18th century by the famous German philosopher Kant that these might actually be other Milky Ways, other galaxies. And also the famous German naturalist Alexander von Humboldt thought so. He called them island universes. But most astronomers didn't want to believe that at all. They thought, you know what, these are solar systems in formation. Probably. Nobody could really see it very clearly because there were no photos yet, right? So you had to draw it. And it could be. But as soon as people started taking pictures, then it didn't really look like that. It was more complicated, and especially when the telescopes got bigger and the pictures got better, then you could discern stars there. And it was something else, but I didn't really know what it was. Now, at a certain point, and that was a culmination of a lot of discoveries among astronomers, but I think the big breakthrough happened with Edwin Hubble, is that he found an answer to that question. And here you see him with his famous Hooker telescope on Mount Wilson, it's in California. Hooker was an industrialist who had made a lot of money, and astronomers succeeded in convincing him that it was a good idea to donate a big telescope so he would be immortalized, right? And that happened in the end. So that's how astronomy developed in this country. Basically generous industrialists who provided them money to do all these new discoveries. Now, what was it that he discovered? It had already been discovered by another astronomer, Sliver from Harvard, I think, that if you look at these nebula, that you can find something very peculiar, namely so-called redshift. This is the light of such a nebula, and it has these stripes here. It's a bit like a barcode, and they indicate the presence of certain chemical elements. And you can also put, let's say, in your photograph, you can put the standard picture lines that you have in the lab, so you can put in different lines of different chemical elements. So here you see these lines here, and they're basically more or less the same place as your standard lines. However, the further away they are, at least that's what you think, because the smaller they are, probably the further away, then you see that these lines are moving to the right. And that means in this case a lower frequency, a longer wavelength. So, and the smaller they are, the more these lines are moved, and that is strange. That was really strange. And it was explained by the Doppler effect. The Doppler effect is when, for example, a car moves, and when it moves towards you and it has this horn blowing, then you hear the tone a little higher pitched than it would be stationary. And when it moves away from you, the pitch is low. Basically, the waves get compressed towards you and they get sort of longer moving away from you. So this was interpreted as a Doppler effect in the sky, that these things were apparently moving away from us, and the smaller they were, the faster they were moving away. Now that was a discovery that attracted a lot of attention among astronomers. Hubble was in the audience when he heard that, and he decided to go after this after Sliver had basically given up doing more research. And he found a way of determining the distances. I'm not going to go into how he did that, but it was a rigorous method based on evidence, just like the redshift is based on evidence. And what he found was that if you look at the distance as determined through the telescope, and you look at the velocity that these things are flying away from us, then you get some kind of a straight line. He did it together with his assistant, Milton New Mason, who started his life as a mule driver, because at the time they were using mules to go up to Mount Wilson and bring up all the materials, but he turned out to be first a good janitor and then very good at handling the telescope, probably better than Hubble himself. So they started cooperating, and they did a great job in getting all these details. And they did it with photographs, right? You could not do it by just looking at a telescope. You needed pictures. So that was very interesting. So the farther away these things were, the faster they were flying away from us. Now, does that mean that we suddenly find ourselves in the middle of the universe with all these things flying away from us? It looks like it. But if you look at, let's say, a two-dimensional picture of what is probably happening is when you blow up a balloon and you look at just one point, when you blow it up, then you see everything is receding from that one point. It's happening here also. You can just pick whatever point you want, but everything is receding from it. So that's happening also in 3D. Everything is receding from us, but if you were in another galaxy, that's what you would see also. So the whole universe is apparently expanding. We're not in the middle. We find ourselves in an expanding universe, and if you think that it's expanding now, then yeah, what happened earlier, if you take it all the way back, it must have had a beginning somewhere. All right? That is something that Hubble didn't really want to believe. He didn't want to speculate on that because he felt if you go into all these crazy speculations and it becomes attached to my measurements, that's not a good idea. It may compromise my measurements, and he was very careful about not letting that happen. But others were speculating, especially a Belgian priest, Georges Lemaitre, who, not because of Hubble's measurements, but because of something else, namely Einstein's theory of relativity, started speculating about these things. Because Einstein had formulated his equations, and it turned out that if you try to solve them, then you would find yourself in an expanding universe. That led to a whole discussion that I won't go into. Einstein didn't like that one bit. He tried to prevent it from happening, so he added a special factor, or lambda, to make sure that that didn't happen. But then someone else came, Alexander Friedman in this case from Russia, who showed, yes, it can still happen. And that was very upsetting because Einstein believed in a static universe. But then this priest thought, okay, that's a good idea, because if you have a universe with a beginning, there is still room for God, right, who has created everything. Now that led to a lot of discussion among astronomers, because quite a few astronomers didn't want to make room for God at all. So they kept hanging on to a static universe. And it's only as a result of more and precise measurements that this let's say, new image has prevailed. And here you see Einstein looking through the telescope, his Hubble in the background and the director next to him. He came over at a certain point to California, and of course he couldn't see anything. You needed photographs to do the science. But it impressed him because there were these empirical measurements there. And basically that meant you have to give way. If your theory is not according to the evidence, then the theory has to go. You know, I have to respect the evidence. That's the point here. I think big history is evidence-based. It's theory-based, but it's also evidence-based. It's not one or the other. You need the evidence. So after this, he decided, okay, yes, an expanding universe. It's there. My equations told me so, but I didn't want to believe it. Anyway, now then people start speculating, what did this early universe look like? What did it look like? How would we find out? Well, you can apply the knowledge of physics and decide if that would help you. That's what they started to do. So if, let's say, the universe is expanding, that means it's cooling, because everything that expands cools down. So if it were basically in one little clump, this primordial atom, then it must have been extremely hot at the time, and it must have cooled down over time. So that is what you can basically say, and that idea is that after all, let's say, the more basic elements had formed, all positive and negatively charged, at a certain point, about 3000 degrees Kelvin, with the expansion going on, it would have cooled down. All the negatively and positively charged particles would have found each other, combined. The universe would have become neutral, and as a result, the radiation, which was present also, suddenly could flow more or less unimpeded. Now, over time, as the universe expanded, this radiation wavelength would have become longer and longer, so you could calculate that basically you would expect a cosmic background radiation of about 5 degrees Kelvin. That's how they describe it. That's the temperature that a black body would emit, that kind of radiation. And these were George Gamow, Russian from Russia originally, and Ralph Alpher and Robert Herman. They predicted that. They wrote an article about it. Nobody checked it. It was just an interesting speculation. But anyway, and then in the 1960s, as part of the space race that had developed, there were all kinds of attempts to create satellites for communication. Of course, now we are used to satellites with radio transmitters that you send up information, they relay it somewhere else. That is the system that prevailed. But at the time, nobody really knew whether that would work very well. So different ideas were also floated and tried. And one of these was so-called echo satellite. Basically blow up a big balloon that reflects radio waves. You can see how big it was. This is a car, right? And launch it with a rocket, blow it up in the sky, and then it would sort of sail over North America from California to New Jersey. And you could send a signal up in California. It would bounce off the satellite. You would pick it up here in New Jersey. And that's how you would try to communicate. That's how the idea was. Now these guys were in charge of trying to make sure that the antenna worked, and they found that there was an inexplicable hiss in the antenna. Something they couldn't understand what it was, and they tried everything to get rid of it. might be pigeons sitting there and whatever. I mean, try to get out all the pigeons. Didn't make a difference. So at a certain point, they decided to call Princeton, and they found an astrophysicist there who was actually working on the problem and was basically setting up experiments to try to find that cosmic background in radiation, because that's what it was. They discovered it. And it wasn't really 5 Kelvin, it was a little lower, but it made possible suddenly to put an age to the universe independently from the measurements that Hubble had made with his expansion. And these things sort of, I mean, you need both actually. It's not completely independent, but it helps you to calibrate it. And that has led to the idea that right now it's 13.7 billion years old. So what you have is suddenly a universe that has a history, it has an absolute age, very, very different idea than what was before, a static universe, no history basically. At the same time, what you get also is that people were able to date rocks. They do it with nuclear fission that happens spontaneously. So some of these chemical elements are not stable, they fall apart. It takes a certain amount of time, you know exactly how long it takes, and then they leave other products as a result. So if you use that to, let's say you measure all these different products, you combine that information, then you can calculate how long that rock had existed, where that stuff is. So as a result, you could suddenly date rocks, and as a result also fossils. And it turned out that the Earth was 4.65 billion years old. I'm telling you everything in a very simplified way, but that's basically how it worked. So suddenly the Earth had a history, and the universe had a history. You could combine that. And I would not say that all astronomers were equally sensitive about these things, but there were certainly a few, and especially most notably Harlow Shapley from Harvard, who realized, we have to redefine the place of humanity in the whole scheme. We can do that now. And he started writing books about it. And these are 2 of his seminal books, one in 1958, as you can see, and one 63. So it was not so much in the humanities that people started to redefine it, it was the astronomers who did it. And there was another man very interesting man, Robert Jastrow, a scientist, originally a very traditional physicist, but then you got NASA and the space program, part of the space race, and they wanted to know what kind of science can we do in space. And as a result, Jastrow got a job to organize that, and he started talking with all the different disciplines that were involved. So what could we do? What can we do about life? What can we do about whatever? So he came up with a whole program. He was in charge of that. And at a certain point, he said he realized that he was basically putting together a new history of everything. So I'm not really sure whether he was aware of Shapley's work. I just don't know. But he wrote his book, Red Giants and White Dwarfs, which is also just, let's say, a big history with an emphasis on everything up to human history, not a detailed account of human history attached to it, but definitely everything else combined. So that was 1967. So these people were redefining our position in the cosmos. And then came this flight of Apollo 8 that I mentioned already, and people were going to the moon and looking back at the Earth. And recently I found on YouTube the CBS broadcasts of the flight of Apollo 8. You can find most of them on YouTube. And it's very interesting to see how people were talking at the time, how these perceptions were changing during that flight. And I want to show you two people who were interviewed. This is John Glenn. I guess you may know him. He's the first American who orbited the Earth 3 times, and it was in 1962. And this is what he had to say on, let's say, thinking big. I hope the sound works. I had to jack it up a little, I think. Let me try to do that. There's a bit of a hiss, but that is inevitable. That's part of the system here, I'm afraid. Let me see. There we go.
I think oftentimes, too, this feeds over into other areas. People think, when they get used to thinking big in a science area, maybe they think that other things possibly are not too big to consider and think about, too, such as can we solve some of our social problems? And they tend to think more widely, and I think there's a general influence possibly that goes far beyond just the scientific influence in the space program.
So that was John Glenn, and now on the next slide I will a short excerpt from an interview with Robert Jastrow. He was presenting, let's say, his case, thinking big.
If I might just widen the focus of our discussion for a moment, you answered the question as to why we're looking into the moon for information. That is, because we want information about the origin of this planet and perhaps the other planets in our solar system. But why, again, do we need such information in this fast-paced life we lead these days?
I think that there are two answers to this question. The lunar landing is not an end in itself. It was a means developed under President Kennedy originally for achieving a manned flight capability that the security of the country required at the time, and which has since turned out to have scientific and commercial and financial applications. That's the main thrust, the manned flight capability with the lunar landing as a means of getting us to that end. There is a long-range aspect to the lunar landing in which it plays its own role. The human species has been on this earth a few 100,000 years, and it comes at the end of a history of life that stretches back to the first billion years of the Earth's history. We have another 4 or 5 billion years to go on this planet before the sun becomes a red giant and vaporizes us. Long before then, we will have ventured out beyond the solar system if we survive, and begun to explore other Earth-like planets, of which there is evidence that there are a great number, perhaps billions, in our galaxy. Mankind is on a watershed. We are crossing into a region of our development in which we can move off the face of our planet for the first time. And the trip to the moon today marks the crossing of that watershed. It is a step whose long-term significance must be judged in the scale of hundreds of thousands, perhaps of millions of years. It will be written very large in the history books, I think much larger even than the politics of 1968 and the problems of the cities.
Right, that was Robert Jastrow. No beating around the bush here. I mean, very precise, very clear. An example of thinking big that hadn't existed before. I mean, this is all entirely new, and I'm very jealous just watching all of this. We didn't get it in Holland. We didn't get a type of discussion. So you were very lucky here to have these great scientists. And then when the astronauts returned, what they came back with is that picture that had shaken me to the core. But I was not the only one, as you can see. I found it much later. This was basically the result that the astronauts presented to then President Lyndon B. Johnson. You have to keep in mind that this flight was meant to go to the moon, right? Prepare for the moon landing, to find out about the moon. It was not about looking back to the Earth, but that was the main result in the end, I think, if you think about its long-term significance. Anyway, and then I think that was the time when other people started doing these things. I think Carl Sagan with his Cosmos TV series that some of you may have watched also is in a way a big history. He didn't use the term, that was coined later, but yes, he popularized it. Lots and lots of people watched it, and it must have influenced the whole culture. So that was when people started doing it, and I think people like David Christian probably unwittingly used this kind of knowledge and then rigorously combined it with an account of human history, and that was new, I think, and that has made possible. Oh yes, the hiss. Yes, I'm sorry. Yeah, I'm just too carried away. But thanks for mentioning that. You're absolutely right. Thanks. Okay. So that is when I think big history as a rigorous discipline emerged, that you combine all these different fields and you get an account of it. Now a few words about recent developments, and then I will continue with my account of big history. First, here you see our little group of 7 big historians gathered in Italy in a place called Gubbio, actually. That's where we are at that point, but we decided, that was last year, to start an international big history association because we felt there's enough traction, enough gravity, so to speak, to do that. There's so much interest now being generated. So these are David Christian from Macquarie University. This is Walter Alvarez. You may have heard his name. He is known for the hypothesis that he developed with his dad, that a meteorite might have killed off the dinosaurs and made room for mammals like us. And here we are actually at the point where he found his evidence. This is the layer where he found evidence that a meteorite might have struck the so-called enriched iridium layer. So that's where we're standing right there. This is Craig Benjamin from Grand Valley State University in Michigan, Barry Rodriguez from University of Southern Maine, Cynthia Brown of Dominican University in San Rafael. Well, that's me, it's my son, and here's Lowell, right, from Villanova. So we started Big History Association. We got elections, and I became vice president, Lowell's secretary, and right now we have already more than 100 members. We formally incorporated officially, and we're hoping to have our first big conference next year in Grand Rapids. And there are some developments that sort of stimulated us to do that, and this is one of the developments. Here you see David Christian together with Bill Gates. And Bill Gates got interested in big history a couple of years ago. I think it was in 2008. David had made an audio series of his book Maps of Time, and Bill Gates listened to that while he was working out on his home trainer. And he got so excited about it that he called David and made an appointment, and he proposed that perhaps they could develop a website together for teaching big history in secondary schools, because Bill felt that if everybody had known this, if he had known this, it would have made such a difference, so he felt everybody's got to know this story. So that's happening right now. I'll tell you a little more about it. And as part of that, the TED conference in March this year, there was a session on what was called the knowledge revolution, and David did a 18-minute presentation on big history. You can find it on the TED site or on YouTube. It's got at least 200,000 hits, I think, which is a lot for a science talk. So that is all happening. So this is the site. This is, I left it here because you see Bill Gates here, but I think they put another message in recently. But this is the site from where you will be able to basically teach big history at secondary schools. They will put in all the materials, will all be free. The first trial run with schools in the US and Australia, it's just started, at least in the US. In Australia it will start in January. It's the Southern Hemisphere, so they have a different schedule. And then they will do another trial run with schools from more countries, one of them from Holland, in which I am involved, obviously. And then they will open it and everybody can use it the way they want. So that's happening. Well, here you see that's another recent development. This was last June. Here we were invited by your former Vice President Al Gore, who convened a small group to discuss what are the current drivers of global change. What is happening in the world? How can we understand it? Here you can see David. Oh, that's me, of course, with a small group of people at Harvard. Well, that was a great honor, of course, but I got that email. Couldn't believe it. I thought, it's a hoax. It cannot be true. So I checked all the data, all the email addresses that he mentioned, and it seemed to be correct. So, okay, yeah, sure. Okay, that's happening. Now, this is very exciting, of course, that these things are happening. There's more happening. Cynthia Brown, who's teaching big history at Dominican in California, there the whole university is going big history, basically. It's a required course for all freshmen. And not only that, and subsequently all the teachers are asked, basically almost required, to put their own subject into the perspective of big history. So whatever you're doing, whether it's literature or French or whatever, put it into a big history perspective and see what you can come up with. So that's very exciting. I mean, basically the whole university is going big history there. That's a great development, of course. So that is all happening. And there's more happening. Actually, this morning I got an invitation to do a short big history course in Guadalajara in Mexico as a result of the Spanish translation of my book. So that's, I mean, it's spreading around the world. Things are happening. Okay, now let's continue with the story of big history itself. So if you think about telling the story of big history, you also have to think about how do we do that? Well, how do historians do it? Basically, most of the time they produce some kind of a story, a narrative, how things happened. More or less structured, often not completely clear on the basis of what this was constructed, of course on the basis of evidence, but why was certain evidence included, why was certain evidence not included. It's not very clear, it's left to the imagination of the historian, and that's basically what happens with most histories. So that is there's nothing wrong with that, that's simply what people do all the time, not only professional historians. Most people tell shorter histories, smaller histories, like, gee, you know what happened yesterday to me? That's also history. There's also a selection process going on there, what you think is important, what you think is not so important. That's how most histories are told. However, you can also try to do it a different way, and that is a bit more related to what people do in the natural sciences, that you use some kind of a theory that structures your story, that makes it more clear how the selection process worked. It makes it also possible to do some testing. So have some more structured discussion about it. If you do a narrative, then you can end up in endless discussions about this or that without having a real handle on it. But if you have a theory, you've got a grip on it, and you can say, okay, what's the evidence for the theory? How does that work? Sociologists do it that way sometimes. Anthropologists, it depends. Sometimes they do it. Some historians do it. And I propose with others that we definitely do it for big history. That seems very important. So that's what I'm going to do now. I'm going to tell you what basically is the emergent consensus among big historians of how big history works. Now, if you think about everything, then of course all the terms must be very general because they must be applicable to everything. And you can think of the history of everything as the rise and demise of complexity. You can think, okay, what is complexity? Very hard to define, but it is something that is more than the sum of its parts. Like you and I, we are more than just the sum of the atoms and molecules that we're made of. Right? We're a little more than that. That is our complexity. And you can think of complexity in all these ways. You can think of a rock as more complex than its constituent molecules, or the sun, or a planet. So you can think of everything as complexity, and then you can ask the question, how did that emerge? Why did that happen? And why does it sometimes disappear again? Right? But let's first consider the question, how common is it actually in the universe? And I think you have to realize that the universe is a pretty empty place. Most of the universe is not entirely empty, but pretty empty. If you think, for example, in terms of our galaxy, well, if the sun is, let's say, the size of a light bulb, then where would be the next light bulb? Let's say the nearest star. I think from here, somewhere in, let's say, Florida or something. That is more or less the distance in Miami. So that is a lot of empty space in between, right? Even in a galaxy. So if you're in between galaxies, it's a lot emptier. So most of the galaxy is actually completely empty or virtually completely empty. And then there are these little areas where there are forms of complexity. And there is at least one area, one planet, where things are pretty complex. So it's completely opposite to our daily experience, where we're surrounded by complexity. We think it's normal, perhaps, but it's a big exception in the universe. That is very important to understand. And then you have to ask the question, how can it happen at all? Because there's something that's called the second law of thermodynamics, and it basically tells you that everything has to become messy over time, and messier and messier. Things don't become organized by themselves usually, they become messier. So how can it happen that things become more organized? If that is the case, that must happen according to the second law. For example, this cup of coffee, if you draw this picture there, you leave it sitting there, it will slowly disappear, and it will probably never reappear all by itself. Right? And that is the second law of thermodynamics in action. Well, the answer is that you need an energy flow through matter, a very general answer. So apparently you have to give matter a certain push to become more complex. That can happen from time to time, and that's how it happened. And if you think about what is needed to remain complex, then it depends on the type of complexity. If it's rather simple complexity, like a rock swinging through space, that can stay the way it is for a long time if nothing disturbs it very much. So it doesn't really need a lot of energy. However, the sun, in order to keep shining, it does need an energy flow. And the energy flow is provided by nuclear fusion inside. Basically, hydrogen atoms are fused into helium atoms. That yields energy that is radiated out. That's how the thing keeps going. And that also prevents the thing from collapsing. So it's basically a battle between, let's say, the heat going out and gravity trying to push it in. So that's what they call a sort of a dynamic steady state. And that will keep going as long as there is enough stuff to keep the reaction going. So that is a situation more complex than a rock, where you see there's an energy flow needed. And for us, of course, we all need our energy flows, right? We need to eat, we also need to breathe air. If air would disappear, we'd be dead within a few minutes, because that is all needed to keep our complexity going. We need to get our energy from outside and also some matter to keep going. So the greater complexity, you need more energy. But this inevitably produces also a bigger mess. That is the second law in action. All across the board, it must become messier. So if things become complex in a certain area, it must become more messy elsewhere in total. That is inevitable. So that is the case for the entire universe, including our existence. All right, so if you look at our situation, that's the sun basically getting rid of its entropy, which is for us high quality energy actually when it comes down here. If the sun was surrounded by some kind of a blanket, if you could do that, then it would suffocate, it would explode, it wouldn't work, but it can get rid of its energy, and as a result it stays the way it is. But some of it falls into the earth. For us it's high energy, it's captured by plants, eaten by animals, and that is what keeps life going on the earth. And what you have is that low level heat is radiated out into the universe. The universe is empty, it's cold. Thanks to the fact that it's been expanding for so long, it's cold, it's empty. It's a big entropy trash can basically, is it, for radiation. And that's very important, because if we were not living in such a cold universe, life could not exist on the earth. Well, that's what keeps us going. Now you can ask the question, can we measure this? And well, basically you can measure the energy flow through matter during a certain period of time. It's very simple math. And Eric did that, and what you get is this situation here. When you look at galaxies, you basically can calculate how much energy flows through them. That's in these units you get 0.5. Now star, the sun, is already more, and galaxies are lower simply because there's a lot of matter there that doesn't really release energy. Now the planets is a little more complicated. Eric is actually talking about the upper layer of 30 meters of our planet. And then you get the incoming radiation from the sun and also radiation from the Earth's center. And that generates altogether a higher energy flow, a higher power density. Now if you look at plants, you get a higher number. If you look at animals, it's again a lot higher, and brains, it's even a lot more. And then society is a little more complicated. I won't go into that. I'm not completely sure that is a good way of putting it, but these numbers are shocking. I mean, if you intuitively, you would think it's the opposite, that the sun would have a much higher power density than our brains, but it's not the case. So what you see, there's a clear relationship to, let's say, complexity as you would think is greater. I mean, you think a brain is more complex than the sun, and a much higher power density. So a much higher energy flow through matter during a certain period of time. Now you can of course expand that, you can do all kinds of calculations. Eric has been doing that, and that leads to a lot of interesting results. But I want to add another aspect to it, and I think that is my contribution to this story, is that if you think of certain forms of complexity, they always need some kind of, let's say, boundary conditions. For us, that's, for example, we would not want to live on a planet with a lot of gravity, because we would not be able to walk, perhaps not even crawl. We would be flat on the ground, right? We would not want to live on a planet that doesn't have a lot of gravity, because there wouldn't be any air. The planet couldn't keep it. So we wouldn't be able to breathe. We might actually fly into space if we jumped, right? It's very small. So there are some boundary conditions, and there are many boundary conditions for our existence, and that is actually the case for all types of complexity. All types of complexity have certain boundaries, which I call, following this story, Goldilocks boundaries. And it's not original. Many scientists are using this term, but I think I'm the first to systematically use this type of analysis for looking at all of big history. And that is how I've structured my book. The idea is that if you combine Eric Chason's energy approach with that Goldilocks principle, then you get a sort of an interesting theory of everything, historical theory of everything. Now, that's what I will run through very quickly now. So here you see again Eric's picture of let's say, the history of the universe. So what you have in the beginning, according to the modern view, is this Big Bang. Nobody knows really what it looked like. You cannot describe it with physics, but you can describe the period very soon afterwards, fractions of seconds actually. As soon as the laws of physics apply, you can describe it, and what you get is basically first a period when all the heavier chemical particles form, the baryons they're called, and then you get the positive and neutral, and then very quickly you get the negatively charged particles, electrons most notably, and then of course a lot of radiation there. It cools down, these things combine, you get the cosmic background radiation that we've seen, and then things expand, and then gravity kicks in and starts shaping galaxies. And these galaxies, most of them, at least on the large scale, expand, tend to fly away from each other. If they're close by, they may actually move toward each other, collide, combine. So also galaxies may have a very complicated history. Now this scenario, first I would like to show you the picture of Eric and his wife Lola. This is the design that they made. She made the design actually for him, and they have it there on the wall, and they're showing it here. I mean, this is an historic, I think, design, because many people are using it now. Anyway, so if you look at what could have formed after the Big Bang, that's basically only light elements like hydrogen and helium. This is the so-called astronomer's periodic table, the abundance of the chemical elements that there are in the universe. And that is simply the case because the expansion went so fast that other elements didn't have any time to form. So if nothing had happened, the universe would have existed of hydrogen and helium. With hydrogen and helium you can get, let's say, stars, galaxies, it's all possible, but life is totally impossible. We consist of other elements like carbon and nitrogen, oxygen, right? That's all very important, calcium. So where did these other elements come from? And you can see they're far less abundant. They're pretty abundant here on the Earth, which shows again that the Earth is an exception in the universe. Most of the universe doesn't exist of these elements. So that begs the question, where do they come from? And that was solved by a British astronomer, Fred Hoyle, who was very much against the Big Bang. He coined the term Big Bang in a radio interview to sort of ridicule it. He thought it was nonsense. He didn't want it because he didn't want any room for God in science. But anyway, he lost that battle, but he came up with a wonderful answer to where these chemical elements come from. Now what you get is that if you get this nuclear fusion in stars, like what's happening in the sun, then after, let's say, most of the hydrogen is converted into helium, then helium can start to burn if the sun is big enough, the star is big enough. And you can get elements all the way up to iron, because that still releases energy. So if your star is big enough, it can make lots of chemical elements. And then sometimes these stars are so big that after everything that has been burned is gone, then they first implode, and then as a result of the enormous heating up, because of the implosion caused by gravity, they blow up. And that creates the Goldilocks conditions for forming heavier elements like gold. Things. So if you have a gold ring on your finger, that was formed in so-called supernova. I mean, that is what happens. So that everything is basically forming. So all these elements then sort of spread into space in a galaxy, and if they're taken up by hydrogen clouds, which contract to form a new solar system with a star in the middle and planets around, then you can get planets that consist of heavier chemical elements like our planet, and then you get the Goldilocks conditions for the emergence of life. So if you look at, let's say, the story like this, if this is our galaxy, then there is a so-called habitable zone in the galaxy. This is a picture from Eric Chason's astronomy textbook. And the reason that there is such a habitable zone is that here in the middle there simply have been too many stars that blew up like supernovae and spread the stuff through space, but you wouldn't want to live very close to a supernova, would you? Because you would be completely blown to smithereens. So if there are too many supernovae in a certain environment, then life will not exist for long. However, if there are too few of them, that's not good either, because you wouldn't get enough chemical elements that needed for life. So you have to be somewhere in the middle, and that's the Goldilocks condition for life to emerge. So that's the reason why we find ourselves in the suburbs and not in the center. Now you can tell a similar story for our solar system. You wouldn't want to be too close to the sun because it would be too hot. So Venus is too hot. It's 400 degrees centigrade or something. It's pretty hot there. I mean, no life is possible. Mars, perhaps, it's beyond the Earth. It's a little cold there, but it may be possible. Beyond Mars, it's very difficult. There may be life possible on moons, Saturn and Jupiter, and perhaps very exotic life on Jupiter itself. You cannot exclude that. But life as we know it, that needs liquid water on the Earth, that is basically mostly possible here. So we find ourselves in the Goldilocks zone, not too far away, not too close. Right, now if you look at the Earth, there you see basically that all the heavy chemical elements basically sunk to the middle, pulled together by gravity, and what you have is the lighter elements that you find on the crust. But in the meantime, meteorites keep adding materials to the Earth so that you also get some heavier chemical elements in the crust. This is pretty hot because in this area there is nuclear fission going on, heavy chemical elements that fall apart like uranium and potassium that release energy. So that is causing, let's say, the Earth heat to come from the center and go into the universe. This has decreased over time by about 90%. So it's only 10% right now of what once was, and it will get colder and colder. It is driving certain processes on the Earth. a very important process that might have driven the origin of life. But what you have also is, of course, the sun that radiates energy. That's a lot more than Earth, than geothermal energy. So we have a bit of a complicated system. We have on the one hand energy coming towards us from the sun and other from inside. That is a more complicated system than the sun. Now, and that has basically powered both geology in the process of plate tectonics, all these moving plates that emerge at a certain point and moving around. That is powered by geothermal energy from inside. And at the same time, you can say most of life, not all of life, but most of life is powered by the sun. Right? Plants capture energy from the sun, animals eat it, and they may eat one another, animals. And as a result, you get this tree of life, or whatever you call it, which may also have all kind of complicated connections. I'm not going to go in all these things. We don't have time for that. I mean, I'm telling you the story in a very simplified way. But if you were to follow our course, we would go into more detail and would tell you more about the things. But the important thing to see is that you get all this complexity as a result of certain energy flows, and without it, it wouldn't happen. And also within certain Goldilocks circumstances, which you can very carefully describe. And as a result, what you get is also all these cycles. For example, the carbon cycle. The carbon gets recycled through life. I mean, geology is very complicated. I'm not going to go into it, but it's very important to understand that lots of chemical elements get recycled all the time. There are lots and lots of cycles going on that have developed as a result of the interplay between geology and biology. You cannot understand the Earth just in terms of biology. You cannot understand it in terms of geology only. You have to think in terms of a biosphere where the two interact, and you cannot really separate the two. So as a result, life basically also is constructing more and more over time, I think, with ups and downs, Goldilocks circumstances that are good for other species, sometimes bad. I mean, it all depends. And at a certain point, you can see that happens sort of by itself without any planning. But at a certain point, animals learn to construct their own Goldilocks circumstances, right? Like building nests or webs or dams or whatever. And that is, of course, a new development where they're trying to create an environment that's good for them. Not necessarily good for others, but certainly good for them. Now, and if you look at human history, then I think you can also describe it in such a way. I mean, we started out a few million years ago without any real complexity that we created. Now we find ourselves in a situation where we often surrounded by hardly any nature anymore. I've created so much complexity. This is actually a picture I took in Beijing last summer. And even we have created the complexity and the Goldilocks circumstances to go to the moon, right? No other species on the Earth has done that as far as we know. So how can we describe that in general terms? And the point I'm trying to make is that you have to stop thinking in just terms of events. Events are important. You have to think in terms of processes, things that happened over longer or shorter periods of time. Now, what have we done as humans? First, we started making tools like 2.5 million years ago. And as a result, we could change the environment. We could also change human relations. And that meant that people who did that, they had to make an investment, but they became more powerful as a result. And that is the case with all these energy transitions that followed. And if you become more powerful, those who don't have it have a choice. Either you do it also, I mean, you make an effort to do it, and then you may become equal in terms of power balances. Or if you don't do it, you may become marginalized, you may actually go extinct. I think these are the stark choices you face when you're confronted with such an energy transition. Now, people start domesticating fire. And that's also a major revolution. No animal has ever done that, but humans have done that, and that basically formed the basis of all modern technology that followed. Then people started basically controlling all these energy flows from the sun through plants and animals by agriculture, no longer just living off what they found, but trying to make sure that they could control it. Of course, all these revolutions need much more detail. I'm just going to mention them now, so you get an idea of how the analysis works. And at a certain point, people started forming states about 6,000 years ago. And what is typical of states, what is very different, is that this is the first time in history that people start to get their energy and matter from other people. Like we do. I mean, nobody, I think, here, although I'm not sure, but I think nobody probably living off the land, and that's what your major energy source is. No, we're getting it from other people. Right? So you get, that's a very different situation. Because you look at each other in a different way, and you look at the land in a different way. That's what happened in states. And that is basically the basis of the dynamics of states, I would argue. That is what it's all about. Of course, I cannot elaborate here, but that's what I think happened. And at a certain point, people start to connect all across the Earth within their own lifetime. People start making trips back and forth within a few years from one side of the world to the other. If there's no side of the world, of course, it's a globe. That happened 500 years ago with Columbus going to the Caribbean and everything that followed. And of course, I'm not going to go into that, but it has changed the world completely because people started moving plants and animals from one part of the world to the other, changed entire ecologies as a result. Right? North America is completely different from what it was 500 years ago, for example. And then people started using, let's say, energy that has been stored in the earth in the form of coal and also oil as a result of long geological, biological processes over millions and millions of years that had formed. They started using it to power machines and doing all the things we're doing right now. That started roughly 250 years ago, very new, of course, it transformed the world beyond belief. And then you can argue, okay, 60 years ago, roughly, people started to use information in ways to control all these processes and to connect with each other. And now with the internet, the last 20 years or so, that has made life completely different once again, because suddenly we can communicate almost instantaneously all across the globe. It also has made big history possible in a new way, because that is how I actually found people like Eric Chason. I remember I was living in Laguna Beach in 1998, and that was when Amazon, for me at least, appeared. So they started to have the second-hand book service. So I typed in certain key terms, and Eric's books came up. So I said, oh, I ordered them. I read them. I thought, oh, that's big history. So I didn't know. So I looked up his email address, which I could find, invited him to come and give a lecture, which he did. And that's how we became acquainted. And that's actually how we basically figuring out how many people are doing big history and how we can organize everything, how we get our information. So big history is very clearly linked to that last process of informatization. There's a lot to say about it. For example, it means that right now, as soon as you invent something, it can be copied almost everywhere else very quickly, because it's very difficult to contain information, to protect it. So that means that power balances all across the world are sort of leveling out. That's what's happening right now. I mean, there's a lot you can say about it. I don't have time to go into all these details, but you can see the relevance for human history very quickly. Okay, now in sum, the idea is humans need energy for producing and maintaining all this artificial complexity that they're making, more than any other animal, right? And this generates a lot of entropy, a lot of mess in form of material waste and low-level heat. That's what we're doing. And everybody has to cope with that in one way or the other. Every state, every government, every individual, we all have to deal with this problem. Now, until right now, I would argue, people have relied on all these natural cycles that have developed to get rid of the entropy. You basically dump it in the environment, and the environment recycles it, right? So that's what you do with your material entropy, and your, let's say, your waste heat goes right into the universe. That's big enough. That's not a problem. But that is becoming a problem right now. Now, what can we say about the future in these terms? That is the point I'm going to make as a final point. Now, of course, if you want to know, if you know that you need energy to make your complexity and also get rid of your entropy, then you really want to know how much energy do we have actually, right? That's what you want to know. Now, if you look at the current reserves, and it is controversial, it may be more, maybe perhaps a little less. This is basically what we have. And depending on the estimate of how much we're going to use it. If you look at uranium, it may be more if fewer people use it. And currently with the nuclear industry again in trouble, it may be different. But it's another lot of time, right? It's a few hundred years at most, and then it's gone. So we will not be able to create all that complexity anymore. We'll have to do something else. Well, are there any other options? Nuclear fusion, perhaps? Well, perhaps. Who knows? 40 years ago, they said, okay, in 40 years' time, we'll have solved the problem. Now they're saying, in 40 years, we'll have solved the problem. So I'm not really sure what's going to happen, but to me, 40 years seems like the career of the average scientist. So they're basically saying, at the end of my career, we'll have solved the problem, and this guarantees my career. That's what it sounds like to me. It's cynical, perhaps, but that's what I think. Anyway, are there unknown energy resources? Perhaps. Well, that means if they're not there, we would like to use renewables, right? So how much is there, actually? And this is a picture that sort of shows where the sun is shining the most, because that's where you want to be, right, if you want to harvest solar energy. So this is what you would need to generate enough electricity for US demand. This is basically could solve the entire world's energy problem. And people are thinking about it, are trying to come up with projects to get it going. And as you know, of course, there's one project right now in the US here that's a little bit in trouble. I won't mention that any further, but it's a little controversial, I understand. But anyway, regardless of those kind of troubles, it's inevitable. That's what we need to do, because otherwise we won't be able to make any complexity anymore, right? We'll need it. So we'll need energy for maintaining our complexity, and many ways of doing it. You can do windmills, you can whatever. I mean, there are many ways of trying to extract solar energy, basically, but that's what you will need. And you need to combat the material entropy, all the waste that we generate inevitably. Think about the second law of thermodynamics. I mean, it must become messier, and if you want to clean that up, you will need more energy to do it. Right? So you mean that is a problem that we will face. So the more complexity we make, the more mess we make, and more energy we will need to clean it up. And it will also create another mess, right? So that is the situation we're facing. So what do we need to do that? And the answer is you try to minimize the material entropy here on the Earth, and you try to maximize basically all the low-level heat that you can get rid of in the universe. That's what you need to do. So that is, I think, the general strategy that we need to follow if we want to survive in reasonable health, whatever, on this planet. And of course, I'm not addressing any of the current concerns like the economy, for example, or what's happening in Iraq or Afghanistan. But I do think that this approach provides some kind of a perspective on these things. And I do think also that if you want to analyze the economy, you could do it very well in these terms, and would help you to simplify the picture. I'm not going to do that right now, but if you want me to do it, I'm happy to do it. But basically, this is what I wanted to say. This is the contents of my book. This is how we approach things right now. So thank you very much for your attention.